All right, this is self-check 1.4. Again, students had about 10 minutes to complete 5 problems for an average of about 2 minutes per problem. All right, so for number 1, we have that f is continuous, so we know it's continuous. It's important. We know it's differentiable, and we know it's closed. So we can use all 3 theorems. All right, we also know that f of -2 equals -5, so let's do a quick little sketch. So at -2, I can go down to -5. And if f of 1 is 4, so I get over to 1, and I come all the way up here to 4. So there's a point down here and a point up here. All right. Which of the following statements could be false? So I'm looking for things that could be false. Most of these, that means it's going to be true. Okay, so let's look at A. We need to translate him. There's, for some point, whenever I see C, I automatically translate that as some point. There's some height, and all of these, by the way, are the interval aside from this one, which includes the endpoints. So in that same interval that I was talking about, the height of C is 0. Remember, f of something is the height. So the height at some point is 0. Let me write that down. The height at some point is 0. Another way of saying that is it crosses the x-axis. Well, do I know that for sure? And the answer is yes, I do know that, because by the intermediate value theorem, I know that between this interval for the x's, I have to cross at least every y value once. So between -5 and 4, I cross each of those y values at least once, so I know that I cross 0 at least once. There is at least one point where the height is 0. So that is true. I'm looking for something that's false. That can't be it. That is guaranteed by IVT. I'll put IVT here. That's an IWT. I need IVT. So that is true. There exists a C. There's some point such that f prime of C equals 0. Let's translate f prime of C. F prime of C is the slope at some point. So I'll write that down for us. The slope at some point is 0. And immediately you should be thinking, oh, that's this theorem. There's only one theorem that proves slopes. And you guessed it, it's mean value theorem. So mean value theorem, or again, the 2 things that we need it to be differentiable, which it is. Up here it says it's differentiable. And the second thing that we need to figure out is what is the average rate, because it is equal to the average rate at least once. So the average rate between here and here, to do that, I do my formula, f of b minus f of a divided by b minus a. All right, and I know that this is going to be my second. I'm going to say that this is my b and this is my a. So f of b is the height at b, so 4 minus the height of a, all divided by b minus a. So b is 1 minus -2. So this is going to be 9 over 3, which is equal to 3. So the average rate is 3. And notice here that it says that the slope is 0. If this was a 3, this would be guaranteed, but it's not, it's 0. So this actually could be false. It's not guaranteed by mean value theorem. So almost, all right, almost mean value theorem if the slope was 0. But the slope isn't 0, the slope is 3 for the average rate, the slope of the average rate. Let's look at C. Translate this. The f of C is equal to 3. How does that translate? That translates by saying the height at some point is 3. So very similar to how I translated A. The height at some point is 0. The height at some point is 3. Is that guaranteed? Look at our graph down here. It has to cross through all the points between -5 and 4. 3 is right here, so it does include 3. This is guaranteed by IVT. This is a must be true. IVT must be true. All the ones I'm crossing out must be true. Let's look at answer D, option D. F prime of C is equal to 3. Translate that. F prime of C. So that is the slope at some point. It's very similar to B. The slope at some point is 3. And what guarantees slope? What theorem? That is the mean value theorem. So MVT, and can we use MVT? It's differentiable, yes. Average rate, it is 3, so that is also a must by MVT. Again, remember, we found the average rate to be 3, and mean value theorem states that the average rate, or if a function is differentiable, then the derivative somewhere is equal to the average rate, or the slope of the tangent somewhere is equal to the average rate. All right, so it can't be this one. That's guaranteed by mean value theorem. And lastly, E. And all I need to translate this says max. It says there is a max. And is that guaranteed? It is guaranteed, so I'm going to cross that out. It's guaranteed by what theorem? What theorem guarantees maximum and minimum? If you said EVT, you are correct. EVT is guaranteed because it is continuous and closed. So the correct answer here is B. All right, I can't ask any questions because I'm doing this during my prep period, so there's no students in the background. Let's go on to the second question. All right, so here we're given a list of points in a table. So let's go through and we're trying to figure out what must be true. All right, so the minimum value, I'm going to stop right there. I don't even need to read anything else. There's no such thing as a minimum value if I'm only given points. So without even reading the rest of this, this is a might be true because I'm only given points. So for example, I'm going to just really roughly sketch this. I have a bunch of points. I know these aren't the exact points, and it's saying, oh, you can never get down here. Like, you know exactly, the minimum is right there, it'll claim. And I'll say no, because what if the graph suddenly goes down like this and then goes through the rest of those points? We don't know because we don't have all the points in between the points it gave us. So this one is a might be true. Let's look at number 2. So in that interval, there's some point such that this. Go ahead and translate this. What is f prime of c equals 0? And I do encourage you to pause the video and actually figure these out. That's why I'm giving you these pauses. F prime of c equals 0. This is the slope at some point is 0. So slope at some point is 0. So is the slope at some point equal to 0? Do we know that? What guarantees a slope? Which theorem? We only have 3 of them. And I'm giving the pause again. That's hoping that you think about this on your own or pause the video. Mean value theorem. Mean value theorem is the theorem that guarantees slope. And mean value theorem, can we use it? It's differentiable, so yes, we can use it. Now we have to just figure out what the average rate is. The average rate is f of b minus f of a all over b minus a. And the shortcut is, if I have the same height that I begin and end the interval with, because the interval, again, starts at 3, goes to 7, starts at 3, goes to 7. If I start at the same height that I end at, the average rate is always going to be 0. That's a shortcut there. So I know that the average rate, without even plugging anything in, this is 0. So I know the average rate is 0. I know I'm allowed to use mean value theorem. So this one is a must be true by mean value theorem. So I'm going to put in here, maybe with a different color, it's true by mean value theorem. Let's take a look at number 3. Go ahead and translate this part right here. I know that I'm still talking about the same, or not the same interval anymore. I'm going from 5 to 7. So I'm going from 5 to 7. So in that interval from 5 to 7, the derivative, go ahead and figure out what this is. What is this in terms of the translation? Can you think about this in your head more so than just the symbolic f prime of x is greater than 0? If you said that the slope at all points is greater than 0, you'd be correct. Remember, x means all points. I'll write that down. X is all points. C is at some point. So the derivative, or the slope of the tangent at all points, is greater than 0. And for the same reason, for number 1, we don't know what happens in between the points. It could go up and down 300 times, maybe not so sharp, in between the 2 points that were given, between 5 and 6, and we would never know. It could have a positive slope and a negative slope repeatedly, but we don't know because we don't have the points in between the data that they give us. So this one is a might be true. So the correct answer here is 2. The correct answer is B. All right, moving on to number 3. All right, so the first thing that you should try to translate into English is this. What does that mean? And I guess I can give you the options also. Is this a left-hand limit, right-hand limit, double-sided limit? Which is it? If you said it is a double-sided limit, you would be correct. And what do we know about double-sided limits? Double-sided double-sided limits. What must be true? We know that the limit on the left, I'm going to call it the left limit instead of a limit left. So I'm going to call it the left limit is equal to the right limit. And if you want the symbolic representation, because sometimes you do need to write this down for the free response on the AP exam, that's the limit as x goes to, and I'll let you think about what goes here, limit as x goes to what of a function? X goes to c from the negative side. That's the left-hand limit. And that means you should hopefully be able to know the notation for the right-hand limit. Go ahead and take a guess at that as well. The limit of f of x as x approaches, if you said c from the positive side, you would be correct. That's how you do the right-hand limit. So these two things must be true for a double-sided limit. And it says it does equal a number. If it equals a number, that means it exists. So these two must equal each other. So which of the following must be true? All right, we have f prime of a exists. So this means what? Translate this into English. F prime of a. And a, again, they're using a different letter here, but you can think of this as our c. There's some point, a. Oh wait, no, that's not c. I totally apologize, because a is very specific here. It's the point that we're going to. So f prime of a, the slope at that point, not the limit, but the slope at that point exists. So it's really asking here, is this differentiable at a? And we don't know, right? Because the graph, let's try to do a counterexample for a. Let's assume it just, that's going to be a bad counterexample. Let's assume that it just came here and then it stopped. Well, that would not work because that's not a double-sided limit. So let's try another counterexample. Maybe it was a hole or something like that. Now the right does equal the left because they approach the same height, the height of Mr. Ant. So this is satisfying the condition that the double-sided limit is equal to some number. We'll call this some number L. Now, does f prime of a exist? Well, no, it does not, because in order to be differentiable, so to be differentiable means to also be continuous. Because remember, that's not how you spell continuous. Remember the definition of differentiable. One of the definitions, there's 4 things that will make it not differentiable. One of those is not being continuous, which implies in order to be differentiable, you need to be continuous. I have just drawn a graph here that is not continuous. Look, there's a giant hole there. It needs to be like a giant smooth line, or not a giant, but just a smooth line that's uninterrupted, no holes or anything. If it's not continuous, it's obviously not differentiable. So this is a counterexample to a, cannot be a. And again, we are looking for things that are true in this case. All right, let's go ahead and look at b. The function, f of x, I'm just going to read that as the function is continuous at x equals a. And very similarly to how I just described the reasoning for a, this case that I've just drawn here satisfies the conditions of the problem, that the double-sided limit exists, because the left and the right-hand limit are approaching the same value. It happens to be L, it could be 5 or whatever. It's approaching the same value. So this is a good graph that satisfies the problem, but it's not continuous. Look, there's a giant hole here. If there's a hole, then it's not continuous. So obviously, the answer is not B. Okay, let's take a look at choice C. The function is defined at x equals a. So what does it mean to be defined again? That's a good question. Defined. In order to be defined, you need to have some height for that letter. So if I have, maybe I choose this x coordinate, what is the height? Well, the height is down here. It's some negative number. But if I go to a, remember if I go this value right here, this is a. If I go to a, what is the height? And again, this counterexample works for this problem as well, because at this value, I don't know what the value of a is. It could be here. It could not exist. It could be a DNE. It could be all the way down here. It doesn't necessarily have to be defined. So in this case, it's not defined, so it's not necessarily C either. Now let's take a look at D. F of a equals L. That is the height of a is equal to L. So if that was true, that would mean that there is a point right here. If I went to f of a, then it is L. But logically, you should say, well, if it was equal to L, then it would be defined at f of a. So if I got D somehow, then C would also be correct. These can't both be correct. It's not D. And again, my logic applies here. If I have a giant hole in the graph, f of a does not necessarily have to be L. It might not even be defined. It might be up here. It's definitely not equal to L there. That could be like 17, and L could be 4. It's not equal to L. Not necessarily. It could be, but not necessarily. So the final answer is E, all the above. All right, let's go on to question number 4. All right, so the graph of the function f is shown. We're looking for something that is false. All right, that means that 4 of these things are going to be true. So f is continuous at x equals a. So if I go to the x coordinate a and I look here, it should be continuous at that value. And I look and I see, oh wow, it's not. Look, there's a giant hole in the graph. When there's a hole, that is a discontinuity. It is the opposite of being continuous. So right away, answer is A. It is not continuous at x equals a. It is discontinuous. This is a hole. All right, let's look at B and show why B is true. All these should be true. Let's just double check. And you should double check on the test because maybe you find 2 that are true and then you have to decide and you say, oh, I made a mistake in A. So let's look at B. The function has a relative maximum at x equals a. And we haven't formally defined what a relative maximum is yet, and that's because I'm pulling from questions on the AP exam that cover more than just what we've covered. But you can kind of tell that it's going to be some sort of maximum, and I'll give you kind of the informal definition here. A relative maximum just means at this point at x equals a, which happens to be at this point, that's x equals a, it has some sort of maximum before it has another maximum. So, I mean, right here it is higher than this point here, and then it starts going down again. But notice that this function goes on forever and ever in that direction, well, probably, unless it dips down again. But it is relatively maximum to this area. Once I get over here, then it's not the absolute maximum. So it is the relative maximum, so that one is true. For this area, if I just limited it to this area, that is the maximum. That's kind of what it's trying to say. All right, let's look at C. X equals a is in the domain. So in the domain just means that when I evaluate it, if I plug in a, then I get some height. So if I plug in a, you might say, oh, it's empty right here. But no, you just jump up to this value. So you get this height up here. So that is also true. It is in the domain. It goes up to height. It just isn't continuous. Let's look at D. So it's really hard to see here. Hopefully you can see on your screen, but it's the limit as x approaches a from the negative side, so from the left side. It's saying that the left side is equal to the right side for the limit as x approaches a. And again, in order for that to be the case, they have to be approaching a same height, or the same height. That would be the better way to say that. And notice over here that as I get closer and closer to a, they do approach the same height. Something that would not be equal for the left-hand limit is if you had something like this where you had a giant gap in the graph. So this is not an answer because this is true. It does come to the same value. The left does equal the right. And to say that formally, the left-hand limit does not equal the right-hand limit. All right, and let's look at E. The limit as x approaches a exists. Well, remember, this is a double-sided limit. Double-sided limit exists if the left is equal to the right. So D and E are almost exactly saying the same thing, and both of them are right. So it's not E either. A is false. All right, and finally we go to question 5. All right, so we know a few things. Continuous. There's an open interval and it's differentiable. We have just unlocked all 3 theorems that we're allowed to use. 3 theorems again: IVT, EVT, and MVT. All right, so we're looking for something that could be false. So most of these things, 3 of these things, are going to be true. All right, so let's translate. F prime of C, what does that mean? Go. F prime of C. That is the slope of the tangent to be exact, or the derivative. So the slope of the tangent at some point, C means some point. So the slope at some point is equal to the average rate of change for some C in that interval that we formally defined. So what does that sound like to you? Does it ring a bell? Maybe it sounds like some theorem, because it is exactly one of the 3 theorems that we know. And the theorem that we know this to be is MVT. We're allowed to use MVT because we unlocked all 3 of them using these statements. And MVT, I mean, this is the definition. Like, it's saying, does this happen? Well, yes, MVT applies. So this is true. So it can't be A. We're looking for something that's false. Let's look at B. Translate this. F prime of C equals 0. What does that mean? F prime of C. I just defined F prime of C up here. F prime of C is the derivative, or it's the slope of the tangent at some point is equal to 0. So it's saying, does the slope ever look like this? Does it ever have a slope of 0 at some point? And that could be false. I don't know. I mean, the function could just be a straight line. It could have something like this where it does have a slope of 0. We don't know. So the answer is B. We don't know if F prime of C is equal to 0. The only thing that could prove this is if we could apply mean value theorem if we had values. We don't have any values to check for mean value theorem. Again, review, mean value theorem. You need it to be differentiable. And then if it's differentiable, which it is in this case, you need to check what the average slope is, or average rate, sorry. And then average rate, you use that formula, f of b minus f of a all over b minus a, but we don't have any f of a or f of b or anything in here. So we can't compute this. We just have to take a guess, and guessing is not good enough to use a theorem. So this is a might be true. The answer is B. Let's see why the answer is not C and why it's not D. Both of these have the same reason. These are both true. They have to be because B was false. They're both true because of what theorem? They're looking for minimum and max. Every time you hear min and max, you should think of EVT. So this is true by extreme value theorem. Remember, if you're able to use it, if it's continuous and closed, then you can use extreme value theorem, and therefore both of these are guaranteed. It just says it has a minimum. We don't know where it is exactly. It just guarantees that there is a minimum. It guarantees that there is a maximum at least once. It could be twice. It could be anywhere on there. It could be 1,000 times. I don't know. Well, that doesn't actually make sense, but it's guaranteed at least once. So it can't be C and it can't be D. That concludes all of this self-check 1.4.